Okay, some of these examples might be repeated because I covered this section earlier, but I covered some of the examples that we didn't know how to take the derivatives of yet. So now that we've covered all of the differentiation, we can go through all of these examples again. Okay, so Lhopitals rule basically says that if you have a limit, let me just go ahead and move down to Lhopitals rule. Lhopitals rule says that if f and g are differentiable on an open interval from a to b, and g prime of x does not equal 0 for all x in a to b, if f of x over g of x has the form 0 over 0 as x approaches a, then the limit of f prime of x over g prime of x as x approaches a, and if this limit exists where L is finite or one of the infinities, then the limit of the original function will be the same value. So if this limit was 5, then this limit would be 5. If this limit's infinity, then this limit's going to be infinity. So that's helpful in evaluating limits. So now that we have all of our differentiation rules, we can work all of these problems. So if you have the limit sine x over x as x approaches 0, well, we know sine x over x is 0 over 0 as x approaches 0. So the Lhopitals rule will apply. So basically, you don't take the derivative of the entire function. You actually just take the derivative of the top and put that in your numerator, and the derivative of the bottom, you put that in the denominator. So the derivative of the top is cosine x, the derivative of the bottom is 1. So now the limit of this function, that should say equal to, the limit of this function is now equal to cosine 0 over 1, which is just 1 over 1, which is 1. Now you might remember we actually proved this limit earlier using the squeeze theorem. So that's just another way to show that limit. Here's another example. If you take the limit of natural log of x over x minus 1 as x approaches 1, well, the natural log of 1 is 0 and 1 minus 1 is 0, so this would give me the form 0 over 0, so the rule applies. So if I take the derivative of the top, I get 1 over x, and if I take the derivative of the bottom, I just get 1. So since 1 over x is just 1 over x, 1 over x over 1 is just 1 over x, then I'm just taking the limit of 1 over x as x approaches 1, which is 1. There's some cases where you have to apply the rule twice. So if you look at this one, you get x sine x over 1 minus x to the negative x squared as x approaches 0. Well, the top's going to go to 0 and the bottom's going to go to 1 minus 1, which is 0. So the limit's going to equal 0 over 0 as x approaches 0, so the rule would apply. So here, take the derivative of x sine x using the product rule, and you'll get sine x plus x cosine x. Well, now you know how to take the derivative of 1 minus e to the negative x squared. That's just going to be positive 2x e to the negative x squared. But you're still going to get 0 over 0 if you evaluate this at 0. So let's apply the rule again. If you take the derivative of sine x plus x cosine x, well, the derivative of sine x is cosine x, and you have to apply the product rule to this. And when you do that, you'll get minus x sine x plus cosine x. So actually, what you're going to get is 2 cosine x minus x sine x for the numerator. So here, let me show you. Take the derivative of sine x, and you're going to get cosine x. And then when you take the derivative of x cosine x, well, if you take x times the derivative of cosine x, you're going to get minus x sine x. And then you take cosine x times the derivative of x, you're going to get cosine x. And add the two cosines together, you get 2 cosine x minus x sine x. And so that's how I got this numerator. And then also, if you do the product rule here, and I'll let you do that. Do the product rule with 2x being your u function and e to the negative x squared being your v function, and you're going to get this expression. Now, but what's interesting here, for this one, if you let x go to 0, you're going to get 2 cosine of 0, which is 2 times 1, so that's going to be 2. And then this is going to go to 0, so you're going to get 2 minus 0 in the numerator. And then here, if you let x go to 0, you're going to get 2 times e to the 0, which of course is 2 times 1, which is 2. And then this term's going to go to 0, so you're going to get 2 minus 0 in the denominator. So you're going to get 2 over 2, which is 1. Okay. Another Lhopitals form, or another indeterminate form that we can apply Lhopitals rule sometimes, is where you have infinity minus infinity. And so here, if you let x go to 0 from the right, 1 over x squared goes to infinity, and 1 over sine x will go to infinity. So you have infinity minus infinity. So what we can do is get a common denominator, and we can combine the two terms, getting a common denominator. And now if we take the limit of this as x goes to 0, we actually do get 0 over 0, so now we can apply Lhopitals rule. Well, if you take the derivative of the top, you get cosine x minus 2x, and the derivative of the bottom, I'll let you apply the product rule, but you can get the product rule for x squared sine x. It's going to give me x squared cosine x plus 2x sine x. And so then if you let x go to 0 from the right, the top's going to actually go to 1, so you're going to have 1 in the numerator, but the bottom's going to go to 0, but it's going to go to 0 through positive values. So as the bottom goes to 0, 1 over 0 is going to go to infinity. So that limit is actually going to be infinity. So therefore my original limit must also be infinity. Okay, here's the limit x times the arctan of 1 over x as x goes to infinity. Well, that's going to be infinity times 0, which is also an indeterminate form. But generally what we can do is, there's a little trick we can do to get that in to the proper form 0 over 0. Basically what I can do here is if I take this x and put it in the denominator as 1 over x, well, it's still the same thing, because if you divide this by 1 over x, it's the same as multiplying the arctan by x. But what happens is, by letting x go to infinity, this becomes arctan of 0, which is 0, and then 1 over x goes to 0. So I get the form 0 over 0, and now the rule applies. Well, now we know how to take the derivative of arctan of u. It's just it's minus u squared minus u prime, which is minus 1 over x squared, over 1 plus u squared. So we have 1 plus 1 over x quantity squared. And then we divide that by the derivative of 1 over x, which is minus 1 over x squared. Well, if you simplify this, basically what you're going to get is minus 1 over x squared over 1 plus x squared times minus x squared. But the minus x squared multiplied by this is just going to give me positive 1, so I get 1 over 1 plus x squared as x goes to infinity, and so that's just going to go to 1 plus 1 over 1 plus 0, which is 1. So there you have it. That limit is 1. Now, Lhopitals rule also works for the indeterminate form infinity over infinity. So let me show you an example of that one. So if I have the limit of natural log of x over x as x approaches infinity, well, the natural log goes to infinity as x goes to infinity, and so does x. So this limit would be infinity over infinity as x goes to infinity. So I'm going to apply Lhopitals rule by just taking the derivative of the top over the derivative of the bottom, and I get 1 over x over 1. So I get the limit of 1 over x as x approaches infinity, and we know 1 over x goes to 0 as x approaches infinity, so therefore this limit up here must also go to 0. Now here's a problem that we can actually, the limit is actually 0 times infinity, but we can use a trick similar to what we did a while ago and get it in the form of infinity over infinity. All I have to do, instead of writing x natural log of x, I can write it as natural log of x over 1 over x, which is the same thing. But now as x goes to 0, we know the natural log function goes to infinity, actually negative infinity, but that's an infinity, and then 1 over x as x goes to 0 goes to an infinity. So we get an infinity over infinity form, so we can apply the rule. So basically I'm going to take the derivative of natural log of x, which is 1 over x, and the derivative of 1 over x, which is minus 1 over x squared. Well, 1 over x times the derivative, 1 over x divided by minus 1 over x squared is actually minus x. So I actually get the limit of minus x as x approaches 0, which of course is 0. There's a couple of other tricks I can show you. This limit, the limit of x to the x, is actually the form 0 to the 0. So what we can do is note that we can write x to the x as e to the natural log of x to the x, which is the same as saying e to the x times the natural log of x. Now, from above, we know that the limit of x to the natural log of x is 0 in the previous problem. So if we write this as this limit here, if we write this limit here, the limit of e to the x natural log of x as x approaches 0 from the right, well, that's the same as e to that limit, to this limit, to the limit of this exponent. So e to that limit of that exponent, well, the limit of that exponent, we know from the previous problem, is simply 0. So this is just going to be e to the 0, which is 1. And then one more here, I believe. This one we have 1 plus 1 over x to the x as x approaches infinity is e. You may have been told before that this is actually one of the limits that e comes from. Well, this has the form 1 to infinity. So let's let y equal 1 plus 1 over x to the x, and then let's take the natural log of both sides. So we get the natural log of y is equal to x times the natural log of this. Okay, so if we get the limit of this, the limit of x times the natural log of 1 plus 1 over x, this actually is the form infinity times 0. But we can actually write that by moving the x to the bottom. We can write that as 1 over x. And now this limit becomes the limit of natural log of 1 plus 1 over x. Well, that's going to go to 1. So you're going to have natural log of 1, which is 0 in the numerator. And 1 over x goes to 0 as x goes to infinity. So now we can apply Lhopitals rule to this. And if you take the derivative of the top, you'll actually get 1 over 1 plus 1 over x times the derivative of 1 over x, which is minus 1 over x squared. And then the bottom, you'll get the same thing. And these two terms cancel, so you're actually just going to get this. So, and the limit of this as x goes to infinity is simply 1. So we showed that this limit is 1, but we're not quite finished yet because that's not actually what we wanted to show. We wanted to show what this limit equals. Well, this limit can be rewritten as the limit of e to this power, and then the limit of e to this power can be written as e to the limit of this power, and of course this power can be written as x times natural log of 1 plus 1 over x. But we just found out that this limit here is just 1. So this is just e to the first, which is e. And so that pretty much completes the examples I have to show you for Lhopitals rule. Hope you enjoyed that. Good day.